This array has 1 million items. I'm going to find a specific number inside it in about 20 steps. Not 20,000, 20. The trick is called binary search, and it's one of the most important ideas in all of computer science. But there's a tiny one-line bug that quietly turns it into an infinite loop, the same bug that fails people in interviews. So let's build it visually and get it right. In the next few minutes, you'll see exactly how binary search works, why it's so ridiculously fast, the clean Java and Python code, and the 3 mistakes that break it. No memorizing. You'll actually understand it. Here's the one idea the whole thing rests on. Imagine you're guessing a number between 1 and 100, and after each guess, I say higher or lower. You wouldn't start at 1 and count up. You'd guess 50. Too high. Now you know it's 1 to 49. You just threw away half the numbers in a single guess. Binary search does exactly this. Every step, it throws away half of what's left. One catch, this only works if the data is sorted. Here's a sorted array. We'll use 3 markers. Low starts at the far left, high starts at the far right, and mid sits right in the middle. We're searching for 23. The plan is simple. Look at the middle value. If it's our target, we're done. If our target is bigger, throw away the left half. If it's smaller, throw away the right half. Then repeat. Let's trace it. Low is at index 0, high at index 9. Mid lands here, 16. Is 16 our target? No. Is 23 bigger than 16? Yes, so everything to the left is too small. Throw it away, and low jumps just past mid. New mid, 56. 23 is smaller than 56, so the entire right half is gone, and high moves left. New mid, and there it is. 23. Found. Notice what just happened. 3 steps to search 10 items and most of the array we never even looked at. So, how fast is this? Every step cuts the problem in half. 10 items becomes 5, becomes 2, becomes 1. That halving pattern has a name. O of log n. And logarithms grow painfully slowly, which is exactly what we want. Watch. 1,000 items? About 10 steps. 1,000,000 items? 20 steps? 1,000,000,000? Just 30. A plain loop would need 1,000,000,000 checks. Binary search needs 30. That is the entire reason this algorithm matters. Here's the Java. Low equals 0, high equals length minus 1. While low is less than or equal to high, and remember that equal to, it matters in a second, compute mid. And notice we write low plus high minus low over 2, not low plus high over 2. If nums at mid equals the target, return mid. If it's smaller, move low to mid plus 1. Otherwise, move high to mid minus 1. If we fall out of the loop, the target wasn't there, so return minus 1. Python is nearly identical. Same 3 markers, same logic, just cleaner syntax. Low, high, while low is less than or equal to high, compute mid, compare, and shrink the range. Understand one and you understand both. Copy either one. They're complete working functions you can drop straight into a problem. Now the 3 bugs. Bug 1, the interview killer. Writing while low, less than high instead of less than or equal to. Miss that equals sign, and when the target sits at the very last position, you skip it. The search says not found when it's right there. Bug 2. Writing mid as low plus high over 2. For huge arrays that some can overflow, low plus high minus low over 2 gives the same midpoint and never overflows. Bug 3, the infinite loop. If you move low or high to mid, instead of mid plus 1 or mid minus 1, the range stops shrinking and your program hangs forever. And the silent one, binary search only works on sorted data. Unsorted in, garbage out. That's binary search. Sort the data, check the middle, throw away half, repeat until you find it or run out. It turns a 1,000,000 item search into 20 steps. Here's the line to remember. Binary search isn't about speed. It's about throwing away half the problem, every single step. If this made it click, subscribe. We're making every DSA concept this visual. See you in the next one.